Once we understand the binomial theorem, the rest is fairly easy. We know that when we take a derivative of an x with an exponent, the exponent's number goes down by 1, and we multiply x with the exponent number. We'll say the exponent number here is n. Let's see if we can write it using the definition of derivatives, which, by the way, is the equation right here. Fx equals x to the power of n. Fx plus h equals x plus h to the power of n. So we can replace the xf here with x to the power of n, and the fx plus h here with x plus h to the power of n. Now if we take a close look at x plus h to the power of n, we can see that this exactly corresponds with a plus b to the power of n, formation we use for the binomial theorem, just with different letters. X is a and h is b. So now we know we can apply the binomial theorem and expand this part of the equation. Since we don't know what n is, we'll just leave it as n here. The first term, k equals 0. Anything choose 0 is 1, so n choose 0 is 1, so coefficient is 1. N minus 0 equals n. X has the exponent of n, and h has the exponent of 0, so we can cross it out here. The second term, k equals 1. Anything choose 1 will be itself, so n choose 1 is n. Coefficient is n. And as we've established before, the exponent on n goes down by 1, and the one on h goes up by 1. The third term, k equals 2. We can't really calculate this one, so we'll leave it as n choose 2. The exponent on x goes down by another, and the one on h goes up by another, and the pattern continues. We can cancel out the first x to the power of n with the negative x to the power of n right here. And then we cancel the h from the top and bottom. Finally, we know that this function is continuous, so we can plug in 0 for all the h's. All but one term will cancel out since they have an h multiplied. And now we're left with this one right here. And we can see that this exactly matches what we had earlier. And there we go, that's the proof.